are sketchy, the dynamic reset option is clear. Any system control approach that responds to varying conditions is allowed, provided it supplies no less than the outdoor airflow currently required in the breathing zone. Although it doesn't require any specific approach be used, the standard describes 3 possible dynamic reset control options. Zone outdoor airflow may be reset in response to variations in zone population. This option is called demand control ventilation, and there are many different ways to do it. System-level intake flow may be reset in response to variations in system ventilation efficiency due to changes in zone airflow. This option has been called ventilation reset control in the past, but Standard 90.1 calls it ventilation optimization control. Finally, the minimum primary airflow setting for VAV zones may be reset in response to variations in system intake airflow, which occur during economizer cooling operation. This option reduces reheat at the VAV boxes. Today, Dennis will talk about first 2 approaches, and remember, although the standard mentions 3 dynamic reset approaches, it doesn't prevent designers from using others.
Okay, the first dynamic reset approach we consider is demand control ventilation, which usually applies at the zone level. Standard 62 permits it in any zone, but Standard 90.1 currently requires it in zones with 40 or more people per 1,000 square feet. And Standard 189.1 requires it in zones with 25 or more people per 1,000 square feet. When used, the zone-level demand control option must meet some simple requirements. First, the controls can't reduce zone outdoor airflow to a value that's lower than the area outdoor air rate for the zone, regardless of the estimated population. Second, the controls must provide the minimum outdoor airflow calculated for the estimated zone population at steady state. This allows designers to ignore the dynamics associated with population variations and damper modulation. Third, when the mechanical cooling system is dehumidifying, the intake airflow cannot be reduced to a level that's lower than the coincident exhaust airflow from the system. This requirement indirectly addresses building pressure. And finally, all assumptions must be documented, including a table showing minimum and maximum outdoor airflow for each zone. Actually, to keep a building at positive pressure when cooling, you'd want the intake rate to be no less than the exhaust rate plus the exfiltration rate, even though the standard doesn't go into that kind of detail. But let's move on. Since outdoor air demand varies with population, one way to implement demand control ventilation involves estimating the current zone population. Current population can be estimated in several different ways. For instance, a time of day schedule in the building automation system could be used to estimate population at any given time. This approach is probably not very accurate, but it can work in zones where occupancy is more predictable, like classrooms or cafeterias or churches. Simple binary occupancy sensors can estimate zone population too. A motion detector, for instance, could be used to indicate either design population or zero population. This all or nothing approach may or may not be such a good idea in some zones, but it can be used successfully in zones that are unoccupied periodically, like individual offices, small conference rooms, some classrooms, and so on. Finally, people can actually be counted in some zones. For instance, theater ticket sales or store entry-exit turnstiles can be used to find a fairly accurate estimate of population. Other people counters are also available, but they are usually more expensive. The estimated breathing zone outdoor airflow currently needed can then be calculated using the estimated population. Alternatively, the breathing zone rate can be estimated more directly using CO2 sensors and a simple controller. Since people produce CO2 at a predictable rate, the difference between indoor and outdoor CO2 level has been widely used to estimate ventilation rate per person. And combined with a simple controller, this difference can be used to estimate breathing zone outdoor airflow. I'll show an example next, but first remember this. Differential CO2 alone can't be used to find current zone population. To estimate population, you'd need to sense outdoor airflow as well as CO2 level, then solve a differential equation to find the current population. Most designers don't do that. For single zone systems and for 100% outdoor air systems with modulated airflow, the difference between breathing zone CO2 and outdoor CO2 level at steady state equals the volumetric CO2 generation rate per person divided by the breathing zone outdoor airflow per person. Typical adults engaged in routine office work generate CO2 at a rate of about 0.0105 CFM per person. Both population and required outdoor airflow rate are unknown, but they are related by the CO2 generation rate. So a simple controller based on this relationship can be used to estimate the current breathing zone outdoor airflow required based on the difference between zone and outdoor air CO2 levels. We can design a controller for each demand control zone as follows. Let's consider a 1,000 square foot lecture classroom with a peak population of 65 occupants. A proportional controller, like the one shown in the 62.1 user's manual, can be designed by simply finding the breathing zone outdoor airflow required at peak population and at zero population. This example zone needs 550 CFM of outdoor air when all 65 people are present, but it only needs 60 CFM when the zone is unoccupied, but the ventilation system is still operating. We use the steady state CO2 equation to find that differential CO2 at peak population rises to 1,240 parts per million, but drops to zero at zero population. These values define the endpoints for a simple proportional controller. The controller itself is simply a straight line between these 2 points. As population changes, differential CO2 changes, and the controller indicates a corresponding change in estimated breathing zone outdoor airflow. This corresponds to a change in required outdoor air intake flow for both single zone systems and demand control zones in 100% outdoor air systems, and it can be used to modulate outdoor air dampers directly in those systems. Modulating the outdoor air damper, of course, changes the differential CO2 level and estimated outdoor airflow rate. The controller uses the new CO2 difference to modulate the outdoor air damper until the outdoor air rate balances with the sensed CO2 difference. The population is still unknown, but the estimated intake airflow equals or exceeds the minimum outdoor airflow rate actually required in the breathing zone. The bibliography includes an ASHRAE journal article that describes several similar controller designs, and the 62.1 user's manual shows a proportional controller very similar to the one discussed here. We also covered this topic in the 2005 Engineers Newsletter Live broadcast that's listed in the bibliography. Zone level demand control can be used in multiple zone systems too. In fact, to comply with energy standards, systems might need to provide both zone demand control and ventilation optimization control. We'll come back to zone level control in a minute. First, let's discuss ventilation optimization control, which is one of the dynamic reset options specifically allowed by the standard. Used primarily in VAV systems, it's a strategy that recalculates system-level intake flow as system ventilation efficiency varies due to changes in zone airflow. A typical VAV system is designed to bring in at least the minimum intake airflow required for proper ventilation of the critical zone. Remember, the critical ventilation zone needs the richest mixture of outdoor air in its primary airstream. In a properly designed system, all non-critical zones get excess outdoor air at design conditions. At any part load conditions, if design intake airflow is maintained, all zones, including the critical zone, are overventilated. So Standard 62 permits the dynamic reset of outdoor air intake as operating conditions change without even considering population changes. Since each VAV controller knows its required outdoor airflow rate and senses its primary airflow, the building automation system can collect this zone information and solve the multiple zone system equations to find the current intake flow required. This becomes the new set point for outdoor air intake flow at the air handler, and that is how ventilation optimization control works. We've discussed this dynamic reset option extensively in previous ENLs and in the ASHRAE journal articles listed in the bibliography, so we're not presenting details today. In summary, VAV systems work like this. If designed for worst-case intake airflow, system ventilation efficiency always rises from its lowest value at design to higher and higher values as the zone primary airflows drop at part load. Efficiency rises because less unused outdoor air exhausts from the system. And since they are inversely proportional, as system ventilation efficiency rises, outdoor air intake flow drops. Now, can zone level demand control be combined with ventilation optimization control? Of course. In fact, they must be combined in some cases to comply with energy standards. Here's how it can be done. If some zones use a demand control approach to estimate population, such as time of day scheduling or occupancy sensors, it's pretty easy. Use design population in zones without demand control and estimated population in demand control zones to find estimated breathing zone outdoor airflow. Use measured primary airflow for each zone and the estimated breathing zone rate to find the outdoor air fraction. Then at the system level, using current information from the zones, solve the multiple zone system equations to find the outdoor air intake flow currently required. But what if some of the demand control zones use CO2 sensors to estimate the required outdoor airflow rather than population? In this case, the design path changes a little. Use peak population in zones without demand control and use estimated population in demand control zones that estimate population. Use estimated breathing zone outdoor airflow for CO2-based demand control zones, found based on sensed CO2 and the simple controller previously described. Note that using the simple controller for CO2-based demand control zones might result in some overventilation because in addition to CO2 from outdoors, the primary air also contains CO2 from people in all other zones in the system. If you choose this approach, be sure to combine it with occupancy sensors in the demand control zones. That way, unoccupied zones with elevated CO2 levels won't be overventilated by mistake. As before, use these zone values to solve the multiple zone system equations for the current system outdoor air intake flow. And finally, set an upper limit on intake airflow. Calculations based on estimates can't result in a current intake airflow that exceeds the design value. After all, cooling and heating capacity are based on design outdoor airflow rates. The best approach for CO2-based DCV zones in VAV systems might require a CO2 sensor in both the breathing zone and the primary air supplied to the zone. ASHRAE research to study this is currently nearing completion, so watch for journal articles about it within the next year. To meet Standard 90.1 and Standard 189.1, high occupant density zones must include demand control in some form, regardless of the ventilation system type. Single zone systems can estimate population to calculate both the breathing zone and the required intake outdoor airflow, or they can use CO2-based controls to establish the breathing zone outdoor airflow and to calculate the required intake airflow. Like single zone systems, demand control zones in 100% outdoor air systems can either estimate population and calculate zone outdoor airflow, or estimate breathing zone outdoor airflow using CO2. But the outdoor air distribution system must be VAV, and every zone in the system must include a pressure-independent VAV box to maintain proper outdoor airflow as the demand control zones modulate their outdoor air flow. Multiple zone systems are likely to be required to use ventilation optimization controls. In addition, they might be required to use demand control ventilation in densely occupied zones. Demand control can either estimate population and calculate breathing zone outdoor airflow, or estimate breathing zone outdoor airflow based on sensed CO2 level. In either case, the current outdoor air value for each demand control zone must be used by the ventilation optimization controls to find the current outdoor air intake flow required for the system. Now, let me summarize dynamic reset. Some single zone systems must include demand control ventilation to meet energy standards. We know how to provide it, and it saves energy with minimal impact on first cost. And if any zone in a 100% outdoor air system requires demand control to meet these standards, its outdoor airflow varies, so the air handler can't supply outdoor air at constant volume. The outdoor air supply must be VAV, and as I just mentioned, every zone in the system must include a pressure compensating VAV box to maintain proper outdoor airflow. We know how to do this too, and it saves energy, but it increases first cost. Remember, the standard doesn't allow population diversity credit in single zone or 100% outdoor air systems, so the equipment must be sized for worst case intake airflow, assuming each zone is at peak population, whether the system includes demand control zones or not. I know it's pretty bad when a quick summary takes 2 slides, but multiple zone system designs account for system population diversity, which saves first cost. They may include dynamic reset at the zone or system level to meet standard 62.1, but they must include ventilation optimization control to meet standard 90.1. And if any zone in the system requires demand control ventilation to meet the energy standard, local demand control ventilation can be combined with ventilation optimization control. The result is a multiple zone system with zone level demand control that really works. That's it.
Well, we hope you learned a lot about ASHRAE Standard 62.1 today. As mentioned, there are a number of publications available that provide more information on the material we covered, including the series of ASHRAE journal articles that Dennis wrote. A bibliography detailing these resources is included in your handout. And don't forget about the supplemental content we recorded. Dennis recorded a segment where he explains all the requirements in sections 4 and 5 of the standard. And Paul explains how the standard allows for design based on average population and walks through a few examples. And John expands on his 3-zone example by going step by step through the Appendix A calculations for systems with a secondary recirculation path. The supplemental material is included on the program DVD, or you can view it on demand at our website at train.com/ENL. As always, past broadcasts are also available on DVD, and many are available on demand free of charge. Visit train.com/continuingeducation for a complete list of on-demand courses available to satisfy credentialing requirements. Many of them, including this one, are lead specific. And remember to fill out a survey and let us know how we're doing. AIA members, please remember to turn in your member information to your local site coordinator. And finally, please join us for the remaining Engineers Newsletter live programs this year. In spring, we'll present single-zone VAV systems, and we'll return in fall to present variable speed chiller plant operation. Thanks for joining us today, and we'll see you in spring.